Okay, going on to the last bit of interference by division of amplitude, and it explains what goes on in terms of why lenses appear purple, why DVDs and CDs. So it's getting to the stage now where I've got to explain to a 6th year class what CDs used to be. It used to be the same problem with vinyl records. But anyway, why you get different colours, that sort of rainbow effect on optical discs. All of this is due to another effective interference by division of amplitude. And so that's what we're just moving on to here. So we've got these lenses appear purple because of the coatings that they put on them. The idea of putting a coating on a lens is that you see a lot less reflection coming off the lens, and so things appear less blurry. That's why we use these coated lenses. So it's a question of how do these work? What's the role of interference by division of amplitude in that there? Before we go any further, it's worth mentioning that we need to consider different sources of light. Extended source is like roof lighting. A filament bulb would be a point source, which is radiating out in all directions. So that's what you'd use for inverse square law. Monochromatic is just a single frequency of light, but you could have lots of different waves of different phase, and that's when we use the sodium discharge lamp for the Newton's rings experiment. And you could use an LED is quite a broad spectrum. It's not a single fixed frequency, but a coherent source is generally what you get from a laser, where you'd be getting this, all the waves are in exactly the same phase. It's a much more, for want of a better word, intelligent form of light than just the sort of messy light that you get from normal lighting. So what we're talking about this morning is really working with either monochromatic or many frequencies like you get in sunlight. So one thing we talked already about phase change on reflection. When you're going through a particular medium, if you've got two wavelengths in air, as soon as that goes through glass, you should know from higher that the wavelengths tend to bunch up and you get that sort of effect due to the refractive index of the light. Just going to show you a quick animation which shows that quite nicely. So just got to get that from. Curiously, this was actually written by somebody in Conan Bridge. So you can see there that as the waves run through, when it goes through the perspex, because they bunch up, you're effectively getting more waves compressed in there, and that's going to make a difference to the phase when it comes out. So you've got waves that are in phase when they enter the perspex block, but because these waves are compressed, they've got a shorter wavelength. We've got 1, 2, 3, 4 peaks there, only 1, 2, and 3 there, which means that by the time they come out, you're going to be getting destructive interference because of that path difference. So optical path is the difference so optical path you can get just by multiplying the geometric path or the actual physical distance by the refractive index, and it basically tells you how much further you're going as a wave in terms of your wavelength because you've had to go through that material. So you just want to, next slide on the PowerPoint has got a quick bit about optical path, so we'll just go back to that. So if you've got two wavelengths in air, the geometric path may be 2 wavelengths, whereas if you've got something going through something that distance with refractive index 1.5, then you've got 3 wavelengths. It's been compressed together. So if you want to pop this in fact, no, we'll go back to just in your notes there about optical path. There. Okay, so those two diagrams there. And it's that compression. You remember from when you did this at higher, you had the same ratio, was the wavelength compressed and also the speed slowed down. The only thing that never changes, of course, is the frequency. The frequency is determined by the source. You can never change the frequency of a wave, because if you had more waves appearing, then they would have to come from somewhere. So the number of waves per second, that frequency is always constant. So we're going to be using this idea now with the Newton's rings and the wedge fringes. It was always air that the path difference was happening. What happens if you've got something like a lens coating where the optical material that you're going through actually has a different refractive index? That's why we're needing to do about optical path. If you're listening to this on playback from YouTube, I've got my own class just copying in an extra note, and so that's why there's this pause. Some people are copying it quicker than others. Okay, so move on. This slide will be available later. So the SQA usefully tell you that optical path difference can either be a full number of wavelengths or an odd number of half wavelengths. All that's saying is that if you've got a full number of wavelengths, you're going to get constructive interference. So the two, you're going to get constructive interference. If it's a half, then they're going to come out of phase and you'll get zero or destructive interference, where m's an integer. I think it's one of the most useless bits of equations that they've put on the SQA's formula sheet, but it's there, that's what it means. So if we look at what's going on with the lenses are coated with generally a material that's got a refractive index in between air, which is n equals 1, the glass, which is usually quite a high refractive index. Good quality lenses use a really high refractive index, and they coated with usually something like magnesium fluoride, which has a refractive index midway between the two there. What that means is that your incident wave coming in undergoes a phase change of pi on the outside surface because it's going into a more dense material, and also this time on the second surface because it's a more dense material on the second reflection. So both of the waves coming out are actually, there's been no phase change between the two of them because they've both undergone the same phase change of pi. But what we're after for maximum transmission going in that direction, you actually want minimum transmission or minimum reflection, so you get destructive interference on the way out, which means you've got this non-reflective coating. So how much distance do you need between the thickness of the film to give you that that extra half wavelength to make them destructive interference? Well, because it's there and back, you've got to go quarter of a wavelength in and then quarter of a wavelength back. And so by the time you do that, you've got half a wavelength path difference, which means that you are getting destructive